All right. Good morning, everyone. My name is Tim Murray. I'm an engineer at Google on the RenderScript team. And we're here to talk about writing high-performance applications with RenderScript. So first, I'd like to talk about GPUs in general. So in the past 7 years or so, GPUs have become useful for a lot more applications than just traditional graphics. And the reason for this is that they have a lot of flops and a lot of memory bandwidth versus CPUs. And so they're really good at data parallel tasks that happen to look sort of like graphics. And the market where this has had the most adoption is in high-performance computing, supercomputing, oil and gas, things like that. The current #1 machine on the top 500 is primarily GPU-based, for example. And now in mobile, we're starting to see these programmable GPUs arrive and become useful. But before we go into mobile, I want to talk a little bit about a traditional desktop or server architecture with a GPU. So the first thing you'll notice is that in terms of raw computational throughput, floating point, memory bandwidth, things like that, the GPU dominates the CPU. It's got 4 times the memory bandwidth. It's got 10 to 15 times the flop on a high-end GPU. However, there's a problem, and that's the PCI Express bus. The PCI Express bus is something that all your data has to traverse in order to move from the GPU to the CPU or vice versa. And compared to the speed of memory bandwidth on either device, it's very slow. So a lot of the work in porting an application to the GPU and desktop comes from managing this data transfer overhead and only moving work to the GPU when you can actually amortize the cost of moving data to the GPU. In mobile, things look very different. The first thing you'll notice is that the GPU and the CPU are now in the same package. They share a single pool of physical memory. So there's no more PCI Express bus. That transfer time is gone. However, this does mean that because they share the same pool of physical memory, the GPU no longer has a memory bandwidth advantage. And to further reduce the GPU's advantage, its floating point performance relative to the CPU is now only about 3 to 4 times faster. We're not talking 10 to 15 times faster anymore. We also may have additional processors available to us in mobile. For example, you could have a camera ISP that can do things like color space conversion or basic convolution or something like that. And you may have a programmable DSP on your SoC as well. And you may really want to use these processors when possible because they're relatively fixed function and they may provide very, very good perf per watt. So in terms of architecture, mobile versus desktop is different. And it's different more than just the block diagram ways, too. Mobile has a lot of architectural diversity. In desktop, you have 2 CPU vendors, 3 GPU vendors. In mobile, you have 3 CPU ISAs. Within ARM, you have a number of different ARM cores and licensed ARM cores. You have dramatically more GPUs and GPU vendors. And particularly within the GPU space, the architecture of these GPUs are very different from one another. If you look at kind of desktop GPUs, at broad strokes, they look mostly similar. That's not true in mobile. Some of them look very CPU-like and have very small SIMD widths and things like that. Others look more like traditional desktop GPUs, and then they have very wide vector widths. Others look sort of like a pool of fixed function hardware. And additionally, in mobile, you have concerns about system resources. The biggest 2 there are power and thermal constraints, which generally don't affect you as much on desktop. You also have issues like the GPU may be busy rendering a lot of pixels. For example, on the Nexus 10, we have a 2560 by 1600 display, which is equivalent to a 30-inch desktop monitor. And we're trying to drive that on a GPU with 80 gigaflops instead of over a teraflop. And you may have additional processors that you want to use as well. So our goal here is really to develop high-performance applications for these wide variety of SoCs without sacrificing performance portability, without guaranteeing that the more you optimize for one SoC, the worse you run on certain other SoCs. So our approach to solving that is called RenderScript. And RenderScript is our platform for high-performance computing across different hardware on Android. So the first thing you'll notice about the API is that the API is focused on the system. You don't get a list of devices. You don't get a big collection of device properties and have to try to figure out at runtime which device you should use. The runtime handles that for you. You simply have a computation that you want to run quickly, and we will try to put that on the best processor we can. What this means is that this gives developers a consistent target that will run well across any SoC. We work with SoC vendors and get drivers for their GPUs and DSPs, ISPs, whatever, and have those available on tablets and phones. And this way, the runtime knows about whatever processors and capabilities it can use. It doesn't require the developer to go in and make all these decisions at runtime about an SoC it's never seen before. We've been influenced by other data parallel runtimes, obviously, but we've kind of taken things in a very different direction. So at a very high-level view, we do look very similar to some of these other data parallel runtimes. We write performance-critical kernels in a C99-based language. These kernels are distributed with your application as architecture-independent bitcode. We then JIT compile those at runtime to one or more processor targets. For example, we may compile them to ARM v7a with Neon, and we may compile them to, for example, on the Nexus 10, we have GPU support in the Mali T604, so we may compile to both CPU and GPU at runtime. We also reflect Java classes for easy integration with existing applications. And what this means is essentially that every time you have a RenderScript file, we generate a set of Java classes that go with it so that you can control execution of that without relying on string-based APIs or having to use JNI or something like that. We also have kind of standard resource management and execution in our Java API as well. One thing I didn't mention here is we also have a collection of, they're called script intrinsics. Essentially, these are built-in, very fast operations that we can tune to specific architectures very well. And they're things like YUV conversion or convolution, stuff like that. Common operations you may use very often where you can get a really significant speed up by tuning very, very closely to a particular piece of hardware. So let's go through some basic RenderScript definitions. The first thing to talk about is the element. So an element is essentially a C type. In this case, it's an int. So it can be a scalar type like an int. It could be a vector type like an int4, float4, whatever. We can also support C structs as elements. So if you declare a struct in your RenderScript file, we will actually reflect an element class for that will be available to Java. So you can use that from your Java API directly. So an element is not very useful in and of itself. So to actually make use of this, we have allocations. And allocations are collections of a single type of element in some arrangement. They could be 1D or 2D. They have an X and Y dimension. And they have a backing store. And that, essentially, an allocation is how you get data from Java into RenderScript so it can be processed by one or more kernels. And an allocation has one other important aspect, and that is the type. And the type is essentially the size of the allocation along with the element used within that allocation. And we use this for two things. First of all, we use it to do safety checking on copies and kernel launches and things like that to make sure that you don't try to copy an allocation of floats onto an allocation of chars because it won't fit. Or a 5x5 allocation of ints onto a 3x3 allocation of ints because it won't fit. We also do type checking when we launch kernels to make sure that the element type passed into the kernel matches what the kernel expects. The other way we use types is to control how much parallel work actually gets launched by a kernel. And we'll get into this more in a bit. So this is a .rs file, a very basic .rs file. And in general, we refer to each one of these .rs files as a script. And a script is essentially its own little world. There's no linkage between scripts or anything like that. So every script is self-contained. And the first thing you'll notice here is that the script starts with two pragmas. First, we have the RS language revision. For now, it's 1. It will be 1 for the foreseeable future. After that, we have a Java package name. And this is the package name that we used for the reflected classes from this script. After that, we have what looks like a normal C99 global. We call that a script global because it is local to the script. And this will reflect a method called setAddVal, which takes an int to Java. So if you want to update this addVal global from Java, you can do that. After that, we have a kernel. And this kernel looks mostly like a standard C99 function, except it has this decorator, attribute kernel. An attribute kernel is the new kernel syntax we introduced in API 17, and I highly recommend you use that. And essentially what this means is the kernel has an input value and an output, or an input type and an output type. And here the input type is an int, so we get an int in, and then we also get two uint32t's, x and y, which are our coordinates within the allocation. And this function returns an int. So essentially what happens is when we run this kernel on a given allocation, for every element in the allocation, this function will be executed. And so at every particular coordinate pair in the allocation, the value of that element at that location will be passed to this function. And then the return value from this function will be written to the output allocation. So because this kernel has both an in argument and a non-void return type, it reflects a method called foreach_kernel. Just it's kernel here because that's the name of the function. And foreachkernel takes two allocations, an input allocation and an output allocation. If you didn't have int in and you simply had x and y, you could it would only take the output allocation. And similarly, if it didn't return an int but simply returned void, it would not need an output allocation. So I want to talk a little bit about a more complicated part of the API where you can do more advanced things. And that is called a script group. And a script group allows a group of kernels to be executed as a single Java call. More specifically, this allows a DAG of kernels to be executed as a single function call. And by passing this, this entire workload to the driver as one monolithic entity before we actually run any part of that workload, we can enable all sorts of different optimizations in the runtime and in the compiler. For example, we can actually enable like parallel execution across devices, or tiling, or kernel fusion, which we'll get into in a minute. We actually see some significant speed improvements today by using script group versus using individual scripts. And in general, I highly recommend that you use script group as much as possible going forward because it is a place where we're going to spend a lot of time optimizing. So let's go through an example of script group. So here we have 5 kernels, and essentially input is passed to A and output comes from E. And then you have this set of dependencies in between. And according to the semantics of script group, the intermediate state is not visible to the user. So all of these connections between A and B and A and C, et cetera, which would normally be stored in programmer-managed allocations, are instead simply set up as connections between these kernels and the graph. And what this allows us to do is the runtime can either create those allocations if necessary automatically, or we can optimize them away if possible. And so we could do things here like, because there's no dependence between B and C, we could run B on the CPU and C on the GPU if possible, or something like that. If we wanted to get more advanced, if we have more knowledge about the way the kernels actually run and the particular dependency information between kernels, we could potentially do something like fusing B and D into a single kernel. And this way, you could simply take the results of some portion of B, depending on how much you actually need to run at a time, and immediately start running that on D. And this is potentially really good for GPUs and also really good for CPUs because it allows you to use things like local memory on the GPU and keep your cache hot on the CPU. So I want to talk about some features coming up in a upcoming release. And the first feature we will talk about is the compatibility library for Gingerbread, and I'll go into that in a lot more detail in a minute. Other than that, we've added rsSetElementAt, which essentially is scatter support for RenderScript. You can now write arbitrary allocations from a given kernel. We have a debug runtime, which does things like bounds checking and prints out errors to make it easier to debug your code. We've added more script intrinsics, things like 3D lookup tables, and I think something else. We have native support for YEV allocation, so you can take a YEV allocation directly from the camera and process that in RenderScript. We've also improved launch latency significantly. So the compatibility library. The compatibility library enables API 18 RenderScript on devices running Gingerbread or higher. And the way this works is essentially we can do a offline compilation of your RenderScript bit code. When you build your app, you can actually create a shared library that runs on the CPU. And we compile this for sort of the lowest common denominator CPU that can run all the way back to Gingerbread. So when the app is actually built then, the compatibility library, as well as the shared libraries for your RenderScript kernels, are packaged with the app. And we also package the normal RS bit code as well. So on an older device, something running between Gingerbread and Android 4.2, we can use this shared library that we've built into the app because it doesn't have API 18. On a suitable device, we can compile the native bit code automatically and use whatever processors or optimizations are available on that device without the developer having to do anything special there. So what this means essentially is that you can have one APK that runs on the Nexus 1 running Gingerbread. And you can take that same APK and run it on the Nexus 10. And on the Nexus 1, it'll run using the CPU shared library. It will run the CPU and run as fast as possible there. And on the Nexus 10, we'll compile the bit code for A15, use whatever A15 optimizations we can. We'll use the GPU, and it'll run a lot faster. And so now, for the first time, you can do all that from one APK. And with that, I'm going to turn it over to Jason Sams, who's going to go through application.
Thanks, Tim. My name is Jason Sams. I'm the tech lead for RenderScript on Android. And I'm going to take us through a simple example of using RenderScript. And then we're actually going to follow up with a more complex example. So the examples we're going to use are going to be a Gaussian blur and a histogram. So for anyone who attended the talk yesterday that Roman and Chet gave, you may have noticed that they were talking about doing drop shadows using RenderScript. And I'm actually going to talk about the primitive they're using to do this. RenderScript, it's been optimized for doing image processing tasks. We've been tuning it for this workload for a couple years now. It's getting pretty good at it. The intrinsics that Tim talked about include a Gaussian blur intrinsic. And so for blurring images or applying other simple operations to bitmaps, it's actually extremely easy to do that, and that's why we'll walk through that example. Histogram will demonstrate some of the more advanced techniques. Things like clipped kernel launches, which is coming up soon. The RSet element at, which Tim was talking about. And we'll also demonstrate multipass processing over a workload. So general image processing in RS and how you go about it. The code to do this is actually pretty simple. And the first thing you'll want to do in an application if you're going to do some use of RS is you'll want to create a RenderScript context. And the first line of our code, we create this context. We actually pass the application context to that. Now, coming up soon, we'll actually have a few additional flags you can pass here, one of which is a debug mode, which you can pass into your context creation, and it'll do things like range check your access and give you additional warnings or errors if it detects something that's not optimal or wrong. But the next step you'll want to do is actually create one of those RenderScript allocations. And typically, if you're doing image processing, your input's probably going to be a bitmap. And so we have a create from bitmap helper function, which will actually create an allocation from a bitmap. And it will automatically set the type and the height and the width of that allocation to that of the incoming bitmap. Now, in addition, you can optionally mipmap that allocation. And we have a few usage flags. Usage shared, it's new or upcoming soon. And it allows us to share the backend store with the bitmap. And that avoids a lot of the copy overhead that you would normally get if you had a separate bitmap and allocation in the older APIs. Also, usage graphics texture, if you were going to use this in combination with RS Sampler, you can set the flag to enable that. And usage script just means we're going to pass it into a kernel. Now, this is actually the default set of flags, so if you were to leave the flags off completely, this is what you would get. For the output, we're going to write this to a bitmap, so we'll create a second allocation. And I'm going to leave off the graphics texture usage because we're not going to sample from it. So we have a bitmap we're going to work on, and we're going to apply a large blur to this. So after you have your two allocations, how would you go about blurring that image? The first thing I would do is I would create a variable to hold the intrinsic script that is the blur. And then I would create that blur script. In this case, since it's an intrinsic, you don't actually have to provide a .rs file. It's built into the system. But you do still need to tell it what type of data you want it to work on. In this case, we're going to say it's a uchar4. That's the element u8_4. We also support just uchar buffers if you had, say, an alpha channel or just a grayscale image. And now we'll take that script that we loaded and we'll configure it to perform our blur. Now I'm going to first set a radius. In this case, we're going to set it to a nice large radius, 20 pixels. So it's going to be a big blur operation. And we'll set on that script the input allocation we created in the previous slide that'll act as our input. And for the blur, we're going to run it. We're just going to call the for each. Since it's an intrinsic, there is actually no name provided. It's just the default for each. And write it to our output allocation. And after we have done that, we need to copy our output allocation back into our output bitmap. Now, with usage shared, it's possible this will be a no-op on some devices and be extremely efficient. And with that, you get a nice blurred image. This intrinsic is actually implemented extremely efficiently. So if you have an ARM device, you get hand-tuned Neon. If you have an x86 device, you get SSE that's been hand-tuned. On some devices, you'll get a hand-tuned GPU kernel. So it really is up to each device how they implement this. But the key takeaway is, on each device, it's pretty much the fastest possible way to implement it on that device. Now, for histogram, this is going to be a more complex example. We're going to present an algorithm that does the histogram in two passes. The first pass will use a large number of workers. The second pass will be a much smaller summation pass. We do this because the first pass, we're breaking the image up into chunks to build intermediate sums. And that allows us to do a lot of work in parallel. And we'll, for the purpose of time, ignore the actual rendering pass into how we draw it on the screen because there's a lot of different ways you could theoretically render this. So how would you write a histogram script? Now, since we don't have an intrinsic, I'm actually going to write a .rs file. The first thing I'm going to do is declare some globals. In this case, they're going to be an rs_allocation type. That is just the script equivalent of the allocation class on the Java side that will hold our input and output data. I will also attach, since it's a multi-pass, an intermediate buffer that'll hold the sums from the first pass. And that buffer will be the number of steps, meaning how many threads I'm going to run to do the summations, and 256 units wide, one for each level of the histogram. And we'll also have a final sum buffer, which will just be a one-dimensional allocation of 256 different levels. So additional globals we're going to pass in will have just integers that will represent the height and width of the input image. And we'll have an integer which will represent how many steps or how many items is in each step of the image and how many steps are in total. So the kernel for the first pass, and I'll have a diagram of how this works in a moment. What this is going to do is it's going to walk over a number of scan lines in the image. However many scan lines will be determined by the steps value. Typically, you're going to see values like 2 or 4. I tried it experimentally, a number of different steps value, and it's very hardware dependent what the most efficient value is. But you can actually pick values that worked across a very large range of hardware. And we're going to actually run this kernel. So you see it takes an x and y coordinate because it's running on a 2D input image. But when we launch the kernel from the Java side, we're actually going to clip it so that it only iterates over x equals 0 and walks through the different y coordinates. I'll go over how we do that in a bit. So the first thing we do for each of these histogram worker threads is we're going to want to clear our output accumulation buffers. And I do that just by walking through a simple loop that sets the sums buffer. It sets our particular line, and then we just loop over the 256 elements. So continuing our first pass, after we've cleared our accumulation buffer, we'll need to iterate over our image. And we do this for 0 to the number of scan lines in our step. Then we calculate which line we're working on. That's the py variable. And if steps is not equally divisible by the number of lines in the image, it's possible we'll need to check for an overrun here, so we'll return in that case, because we'll be done. And then we walk through one scan line. So we just iterate in the kernel from left to right, and we'll get an element from our input image and load that into a temporary uchar4 value. We then calculate a luminance value from that. In this case, it's just integer math, nothing terribly exciting. And then after we've calculated a luminance value, we use that as the x-coordinate index into our intermediate buffer, and we load the existing value, increment it by 1, and then use setElementAt to write it back. And this is how we're constantly accumulating from each work item an output value. So for the second pass, after the first pass, we have basically an image which a number of temporary buffers that indicate however many values of each level were run for that thread. Now we need to sum all those together and get one set of results and not n sets of results. This kernel is a 1D kernel, so it's only going to operate over one dimension. And we just simply loop over within that kernel the input values and sum up one vertical column of levels. And we return the sum, and that writes the output value for that level. So rescale. This is an example of an invocable function. So after we have our buffer that has 256 items and tells you how many pixels of each level it saw, what you may want to do is actually rescale that to some range. In this case, we'll have an invocable. If you notice, there's no declaration kernel on this, and it's going to be called single-threaded. This is good for very small workloads where you don't want to necessarily launch a lot of threads and do a lot of overhead for a very small amount of work. So we loop over, we find the maximum value in terms of any one bucket, and then we just iterate over our buckets and we divide the values there by the greatest value to effectively normalize the range. So what does this look like on the Java side? So you've written this .rs file. What do you actually do with it in terms of interfacing that with your application? Well, the first thing you need to do is load it. The first line here is how we do that. We create a script variable, and then we can just say new script C underscore whatever the name of your .rs file is. And this works because we've reflected a Java file from your .rs file, and effectively you now have a Java class with all the methods that you could use to actually talk to that .rs file. And so after it's loaded, things like the width and the height, those globals, you can just actually call Java methods and it will set those for you. You can set any value you want at that point, but in this case we'll set the width. Now we need to create the allocations to hold our data. We demonstrated earlier how you would create the input and output allocations for the input image and the final image, but how do you create those intermediate buffers? In this case, we're going to have to do it by building a custom type because it's going to be a shape very specific to that intermediate buffer. So we create a type builder. We specify an element of int32, which is just regular integer, is our element type. And then we set the x and y dimensions that we want, in this case 256 wide by steps high. We create a type from that. That's the dimensions of the allocation. And then we actually allocate the backend store from that. So we'll also need to create that 1D buffer to hold the final histogram. And in this case, we'll again choose int. But we have a helper function so that you don't necessarily have to create a type for every allocation you want to create. If it's a 1D allocation, we actually have a helper function that will automatically create a 1D type for you. In this case, 256 elements. And then we set those allocations we just created to the script. So running the first pass. Now, launching scripts from Java, very straightforward, but we're going to do something a little more complicated than we talked about in the blur. If you remember when we talked about the first pass, we said we were going to clip this kernel so that it only ran on x equals 0, but actually iterated over all the y's. So coming soon, we have on the Java side a new option for launching kernels and the ability to clip the kernel to the region of interest that you want that kernel to run on. This is very useful if you want to, either do what I'm about to do here, or if you were just editing part of an image. We create a launch option structure, and then we set the x range. The first value is inclusive, the second value is exclusive, so that's why you see 0 to 1. And then we do our for each pass, and coming soon, not only can you specify the input or output allocation, but we actually reflect overloaded versions of this that will take the launch options, if you so choose. And so what does this actually look like running? So we have the allocation we created. The kernel's going to, in each time, see x coordinate equals 0, and it's going to see a y coordinate that is the number of steps, as we drew earlier. Now running the second pass. So after you run the first pass, the output will be in that intermediate buffer, and you can just immediately call the for each on pass 2, and this will sum the first buffer into the second, and now you have a single allocation which contains your range of values. And we can simply call rescale by invoke. If you notice, this doesn't take any parameters in this example. Invoke functions are actually very useful for things like setup. So if in the .rs file you put some parameters in the prototype for that function, you could actually pass them directly here. However, you cannot return values, so the prototype always must be void. And you have your histogram. So with that, I'm going to open it up to questions, if Tim would join us again. Thanks, everyone. So one other comment, during office hours, I actually have both a ARM and x86 device that can be seen running this example if anyone's curious. But it runs very well on both devices. The good news here is by writing in the agnostic code, we actually generate back-end code that is optimal for all. Hello. Take the first question.
So you had mentioned two things. You mentioned that the ISP and DSPs on some mobile devices. Is there any access to the fixed function hardware, like the fast resizing, the fast color to space conversion you see on ISPs? And then my second question was, are there any plans to have RenderScript run on something other than Android, even if it's Chromebooks or just regular old Linux?
Okay, I'll go ahead and answer the first one. The answer is yes. Part of the reason we have intrinsics is we can use processors that are more fixed function than you can by writing code directly from a .rs or .fs file. And so something like the Gaussian blur we use as an example, we actually have other intrinsics like convolve 3x3 and 5x5. Those will run very well on something like a fixed function ISP or DSP. Another example, that's our YUV to RGB conversion. Again, you should be able to take advantage of that fixed function hardware because it's going to be both extremely power efficient and usually very fast. I'll let you take the second one.
So as far as other platforms, it's possible. Basically, during my spare time in the last 6 months or so, I ported this to standard Linux. It just runs on the CPU, but it was really straightforward. Because we make such heavy use of LLVM and Clang, essentially we can port trivially to any platform that has an LLVM and Clang, good LLVM and Clang support. So in an upcoming AOSP release, you'll see all sorts of if-defs for things like RS server. And if you wanted to construct your own makefile with an appropriate version of LLVM and Clang, you could certainly do that.
Thanks.
Hi. I was wondering when the API 18 RenderScript stuff gets into the compatibility package, will that include the script intrinsics?
Yes.
Okay. Easy question. Oh, second follow-up. When is there any time frame for that?
No.
No.
You can't trick us.
So just to confirm, the Gingerbread stuff is dependent upon 18 coming out, and then the compatibility library will have that, correct?
Correct.
Okay, follow-up is, what memory constraints are there for the size of the RenderScript kernels that you can build?
What do you mean by the size?
Bytecode size, and I was like, if I'm like, how big a function or sets of functions can you build before you might be hitting memory issues, either device dependent or things that you have seen in the wild?
I've seen an entire H.264 encoder written in RenderScript, so the size limits are pretty high.
Yeah, I don't think you'll run into too many issues with code size.
Hi, my name is Mark. I would like to know, more from the graphical side of Android. So there are really high dedicated examples of doing graphics in RenderScript, like for example the page flipping in the ebook reader and in the YouTube app, and I guess the cover flow in the play music is also done with RenderScript. I don't know really. Have you thought of building a website with really high dedicated examples with RenderScript?
So we are trying to improve our documentation and improve our samples. In API 18, you'll see a lot of new and kind of hopefully clearer documentation. Samples we are working on. In general, one of the best places to look right now, we have a test called image processing. You can find that in AOSP. That has a lot of different kernels and can basically give you a good idea of how to write a RenderScript application.
So no website available with great examples here, just the examples in the SDK.
Yeah, most likely. Okay. I mean, that's where we're focusing for now.
You said that you're not going to support anything other than the CPU on Gingerbread. Is there a technical reason you can't do that? I mean, a lot of these old phones have DSPs.
Yeah, so essentially we would need a new driver on there. And we would need, I mean, the way we have our driver work is we're an OS component. And the way we can get around that in the compatibility library is by loading these shared libraries, which are, they're not OS components. So essentially, if we were to try to support anything more than the CPU on Gingerbread, we would have to, they would have to update that part of their OS.
So is there no way to get access to, say, like a TI DSP or anything like that?
Not on Gingerbread, no.
Yeah, the support necessary in the OS simply wasn't there in Gingerbread, so there's really nothing we can do without an OS update.
Thank you.
Okay, thanks everyone. I think we're out of time, so we'll be around for office hours if anyone has additional questions.
Thanks.